Okay, welcome to the recorded session for applications of RSO Satellite Imagery for winter storms. I'm Ed Zoke, and I'll be giving the first part, and then Dan Bykos will take over. Here's an outline of our learning objectives. Basically, we want to give some of our thoughts on what the RSO imagery is showing us in terms of the synoptic scale components of this very intense storm, and also some of the mesoscale features. I'm going to start with an overview of some of the NWP issues that we had and point out some of the areas of greater uncertainty that were problems with this forecasting for this storm. So we're going to focus on one storm in particular, big nor'easter, late January of 2015. I grew up in Worcester, which is where this little black dot is right in here, and they had an all-time record snowfall of 34.5 inches. Unfortunately, I never saw anything quite that large when I was growing up there. So this was a huge storm in many places. You could see Boston, Portland as well. But some of the areas that didn't do quite as high were New York, and we'll talk about that, and of course Philadelphia, where a lot of snow was anticipated but didn't fall. We can't resist showing a few pictures. Here's one from south of Worcester, impressively deep snow. Here's one from Central Park in New York City. Now, they certainly did get snow, but forecasts were as high as 2 feet leading up to the storm. And finally, this montage of pictures, the storm deepened, and it was quite a storm off the coast, and of course that means anything from flooding to a blizzard on Cape Cod, as we see in these photos. Okay, we won't do an exhaustive look at the models, of course, but just to give you an idea of some of the forecast issues, we're showing here is a four panel on the top and the left. Here is the GFS, and then ECMWF on the right, and then the same on the bottom for two different runs. First one on the top here is from 0Z on the 25th, and then the bottom one is 12Z Sunday, the 25th, and you can see that in the GFS. This was, by the way, the beginning, first kind of look at the new GFS down to 13 kilometers, which is roughly what the resolution of the ECMWF is. And you can see that there's a sharp gradient in the precip in this area of, from Albany down to New York City, but distinctly less. And this is a respectable storm, up to perhaps an inch of melted precip, but far less than what the European model was showing, which was over 2 inches of snow in consecutive runs for the New York City area. Now we go forward a day, and this is now getting pretty close. The storm actually begins in New York City on Monday the 26th, and these are runs from 12Z on Monday the 26th. And you still see the GFS showing this very sharp gradient, but basically having from Albany to New York City in about a half inch or so precip, and about double that now. They've backed off a little on the European, but still double that showing up in that run. And the NAM agrees with the Euro. In fact, maybe ups the ante a little with up to 3 inches of melted precip close to New York City. This is just a very rough idea of what fell in terms of melted. And of course, down here in the lower right, whenever you have a storm like this, it's tough to actually get a good measurement of melted precip with all the wind that took place, but you can see the point is there's a very sharp gradient, and it's much farther to the east than what was shown in either the EC or the NAM. So here's another way to kind of look at some of the uncertainty we just saw in those model forecasts, and that's with the Schref model, and these are plumes from the runs on Sunday the 25th, 15Z. And we have Albany, Boston, LaGuardia, and then Portland, Maine. And the red numbers show what actually fell, and the plumes show what was forecast. So you can see for some areas, for instance, check out Boston, there's a rather close clustering on the plumes in here, and that's pretty close to what actually happened. LaGuardia, on the other hand, they ended up with around 11 inches, which is down in here, but you can see there was quite a bit of a spread seen in the plumes. Albany also quite a bit of spread, going all the way up from 20 down to about 5, and they ended up with about 6. Meanwhile, Portland, Maine over here, a much closer clustering of the plumes, and we saw that they ended up with 26 inches of snow. So the Schref plumes at this point are showing uncertainty, we think, where there was quite a bit of uncertainty seen in the other forecasts as well. Okay, here's the plumes for 1 day later, and now again we're really close to when the storm is about to begin, and I guess the main point here is that we still see a nice clustering, for instance here at Boston and Worcester, at some very heavy amounts, and this is where the most certainty was seen in the earlier forecast. But it's impressive how much uncertainty was still being displayed by the forecast, even though we're getting close. Here in Newark, for instance, they only ended up with about this much snow, but you can see a huge spread. Ice slip, same thing, although they certainly ended up with a lot more on the eastern side of Long Island and pretty close to where the average was forecast. But you can see again here, Albany, a large spread, and LaGuardia as well. So this was not an easy forecast, even as we got very close to the event. Okay, here's an overview loop using water vapor imagery and GFS analyses at 500 millibars. We start this off at 06Z on the 26th, so late Sunday night in the East Coast, and watch the trough amplify. The main trough amplifies off the coast and forms a closed low south of Cape Cod. And a second feature that's kind of interesting is a wave that we see coming in and deepening the overall trough behind the system, and I think that helps hold this whole thing in place and stalls it a little bit before it moves off eventually to the northeast. I'm going to stop it here for a second and just point out one feature that we see rather prominently develop is this warm conveyor belt here starting to develop here, and it amplifies as the system deepens off the coast, and we see that rather prominently here. Dan will talk about a lot of the features closer to the coast and in New England in just a moment. And the other thing to kind of note is how quickly, and I loop this one more time, how quickly things changed off the East Coast. There had been a storm on Saturday that moved up the coast. Things dried out tremendously, but then it doesn't take much with all the moisture, obviously, in the Gulf Stream, that this thing, when the next trough moves in, that we get a lot of strong deepening. Here's a couple of, we'll look at some overview imagery first, looking at IR image with the METARs, and we're also going to have the 1 hour cloud-to-ground lightning plots when they show up. This is at 9Z on Monday of that storm, and then this one with a pressure analysis from the GFS at 12Z. A couple of things to note. You just notice in that short time frame, the original low is off in the inland a little bit, and a new storm is starting to develop off the coast. As the trough approaches the coast, we see lightning with the along what is the developing cold front, and then a lot of moisture already taking place off the coast. Another thing to point out is there's a very strong high off to the northeast in eastern Canada, 1034, and in the IR imagery there's a huge amount of cold air showing up here. This is cold and dry air, and this plays a big part of the storm, kind of eroding the back edge of the storm, which made for a very strong gradient in the precip and made, of course, the forecast very tricky at times. Okay, here's a series of visible imagery with this time the RUC analysis of pressure, and again we'll have the lightning data where in 1 hour cloud-to-ground lightning, and we see quite a bit of lightning now by 15Z. Classic deepening of the surface low off the Carolina coast, and look at all this lightning that's showing up now in the warm sector, and then along the cold front down in here, and then back in the cold air behind the cold front. It starts to show up, and then if we advance one more to 21Z, we also see in this visible imagery the warm conveyor belt lightning even approaching to the northeast of the low. This shows the potential for embedded convection that will be showing up in some of the loops that Dan will show in just a moment here. And again, a lot of lightning even back here in the cold air, very strong cold air with this deep trough that is now setting up. Dan will take it from here and look at some of the details of the RSO imagery.
Here's the water vapor imagery during the first half of the event. Early on, we can see the upper low over the southeast, followed by a strong upper jet digging in along the southern flank of the entire system. And what I want to focus in on is this developing warm conveyor belt. I'll go ahead and first remind you of the one that Ed pointed out earlier, this one further to the east. And then soon after this time, we see the development of this additional warm conveyor belt right here, this large area of expanding colder cloud tops. It fills in time and becomes the comma signature that we associate with extratropical cyclogenesis. So the development of this warm conveyor belt gives us additional confidence that we have baroclinic energy, even more baroclinic energy for the system to intensify further. If we overlay the MSLP, we can see the transition of this low that we initially see over the Ohio Valley transition to a coastal low just off the eastern seaboard here and intensify in time. The other thing we see is, remember that surface high that Ed talked about previously over southeast Canada. We can also see in the water vapor imagery the confluent flow in the background water vapor imagery, which provides for an increasing pressure gradient across the northeast. Here's a later water vapor imagery, and at this point we can see the cyclonic branch of the warm conveyor belt peel off towards New England. This is known as the secondary warm conveyor belt, or once occlusion begins, usually referred to as the trowel. The upper low becomes vertically stacked and slows down, therefore heavy precipitation continues over the region of interest. And if we overlay the 500 millibar heights, you can see the jet that wraps around the system here is this region of fast-moving, warmer brightness temperatures that appears to elongate the trough and therefore contributes to the slowing down of the entire system and helping to provide a long-lasting heavy snow event. On the left, we have the synthetic 6.5 micron water vapor imagery from the 4-kilometer NAM nest. And then on the right, we have the corresponding GOES 6.5 micron imagery. The point I want to make here is that many of the signatures we identified in the GOES water vapor imagery can be seen in the model output over here. This is a direct comparison between the GOES and the model output via the synthetic water vapor imagery, and it can provide an assessment of model cyclogenesis evolution. Focus more on the location and timing of the cyclogenesis components as opposed to specific brightness temperatures at a given location. Here's the GOES IR imagery along with the MSLP and also the lightning data at 0Z on the 27th. As the low continues to develop, lightning activity expands northward with that warm conveyor belt, allowing that convection to get closer and closer to our forecast area. On the left, we're looking at the blended total precipitable water product, and on the right, we're looking at the blended TPW percent of normal. The role of the warm conveyor belt is to advect warm, moist air from the warm sector back towards that surface low, as you can see up here, allowing more baroclinic energy for the surface low, which leads to deepening and intensification of the system. The percent of normal TPW product indicates how anomalous this moist air mass is at this location for this time of year, as you might suspect for a moist air mass this far north in January. Rapid scan operations, or RSO, corresponds to 8 images per hour with an irregular time interval varying between about 5 and 10 minutes for the timestamps on the imagery. It was activated by the Boston WFO for this particular winter storm. Remember that WFOs can and should request RSO activation for winter storms, including lake effect snow, in addition to convective events that you're used to requesting for RSO. When GOES-R becomes operational, a storm such as this would likely be covered in a mesoscale sector, such as 30-second or 1-minute time interval. Recall that you not only receive more images, but they display on your AWIPs much faster, approximately 7 minutes for RSO. The IR imagery we're looking at here shows the secondary warm conveyor belt that we mentioned earlier, impacting the region of interest. However, as time progresses, this shifts northward across Maine. After occlusion, which is about halfway through the loop, the secondary warm conveyor belt evolves into what's usually termed the trowel airstream. Recall the TPW imagery that we looked at from 12Z on the 27th showed the moisture plume advecting into southern New England. This corresponds to the last time shown here, which I'll go ahead and stop at this particular time. So the point is, even though the colder cloud tops with the secondary warm conveyor belt have moved into Maine by 12Z, the TPW product still showed a good moisture plume at this time, moving into Cape Cod, where we see this embedded convection move inland and expand in time, and also impact eastern portions of southern New England. Next, what I want to do is increase the speed of the loop, make it rock back and forth, and one of the things that this is useful for is identifying different features in the imagery. For example, in this particular loop, you can really see the edge of a sea surface temperature gradient approximately right in here. Because it doesn't move, we have our contrast between the warmer background and the cooler background brightness temperatures. Finally, I want to stop it at a particular time at 6:45 UTC, and note the region of convection that we see just to the southeast of Long Island appears to be moving towards our forecast area over here. We're going to compare this with the Veers imagery that we're going to look at in the next slide. Here's the Veers day-night band at 6:45 on the 27th, the same time that we were just looking at for the GOES IR imagery. And keep in mind, this is relatively new imagery from the JPSS satellite that makes the unique sensor characteristics along with existing moonlight that allows us to have a visible image at night. In this particular example, there's a half moon which provides sufficient light. Note the individual convective elements as I zoom in here. In this higher resolution imagery, it just displays with a lot more clarity compared to the GOES IR imagery, of course, because of the improved spatial resolution. Also note that city lights appear in this channel. These lights are showing through the cloudy regions due to favorable forward scattering, which makes them more diffuse compared to clear regions. This type of imagery is now available on AWIPS 2, and you can see the visit web pages for additional training links. Here's the total lightning data between 8 and 14Z from the Earth Networks network, and it shows the lightning associated with the convection that we were looking at offshore in the previous satellite imagery. Here's the RSO Visible Loop. We can see the surface low pretty clearly as this tight spiral of low-level clouds southeast of Cape Cod. If we overlay the surface observations, we can see that change in wind direction with this buoy very close to the surface low. We can see remnants of convection wrapping around inland over eastern Massachusetts, and we can note this strong deformation zone that shows up pretty nicely from down East Maine into New Hampshire and eastern Massachusetts. And of course, that's one of the ingredients for mesoscale banding, which we'll assess later with the radar reflectivity. The band in western Massachusetts, moving towards Albany, is weakening in time, and we can actually see a wake of thinning cirrus near the end of this loop. If we rock the imagery back and forth here, along with the METAR as our overlay, we can easily spot the warm front offshore just northeast of the low, extending something like so here, with a zone of overrunning that extends towards Maine and into southeast Canada. Note that the warm front appears quasi-stationary, consistent with what we observed in the overall system water vapor loop, and that is that it's slowing down. We can also see streamers within the low-level clouds, for example, here and here. These may be traced back to land features along the coast. And then finally, by the end of the loop, you can see the various fronts quite clearly. I'll go ahead and stop it right here, and you could actually go a little bit later. Here's our surface low, here's the cold front, and right behind it would be the low-level cumulus associated with the cold air moving over the warmer water, and then we have our warm sector out here. So this actually indicates that in this region just northeast of the low we would have an occluded front up to approximately right here, and then northeast of that we would have our warm front to the northeast of that. So that gives us additional confidence in the evolution of the secondary warm conveyor belt to the trowel airstream, as we noted earlier. Here's a comparison of the visible imagery RSO loop on the left and 15-minute schedule on the right. So this is what you would see on the right if RSO had not been called. Many of the features that we discussed on the previous slide can be contrasted between the 15-minute and RSO loop. More images available in your loop make for a more efficient analysis and also places features in context better. It also reduces the likelihood of missing subtle features, particularly transient ones. Remember, the temporal resolution will improve substantially with the introduction of GOES-R. Here's a later RSO visible loop. The surface low appears to be slowing down, and the occluded/warm front is still quasi-stationary. Note the cumuliform tops in eastern Massachusetts over this vicinity, suggesting enhanced snowfall rates there. In portions of New Hampshire and northwest Maine, you can see enhancements to the low-level clouds, likely driven by orographic effects. And you can see other possible orographic effects here in northeast New York State. Note the development of the band along and east of New Jersey, across this region right here. Likely within a deformation zone, the drier air at low levels likely prevented significant snowfall rates over New Jersey, but perhaps it did snow heavily offshore. Note the clouds over eastern Massachusetts and into Cape Cod. They're barely moving, continuing heavy snow in this region. Remember, it's consistent with the features that we already noted, being pretty much quasi-stationary, leading to this slowing down of the system and a very heavy snowfall. Let's take a look at a couple soundings from 12Z. Albany, New York is in green, Chatham, Massachusetts in cyan. Note the effects of the warm conveyor belt at Chatham in the cyan here, with the warm layer that we see from about 550 millibars to around 700 millibars in this east to southeast flow, which we also observed in the total precipitable water image that we looked at earlier. Meanwhile, at Albany, the warm layer at mid-levels is not nearly as strong in magnitude. However, we do see at Albany this low-level cold, dry air mass in the lowest 100 millibars or so, which may be contributing to evaporation on the western fringes of the system. In the radar reflectivity, we observed the low-level circulation that was observed in the visible imagery slowly moving westward and then stalling. We see a lot of persistent echoes wrapping around the west side of the circulation in the Cape Cod and Boston region. Mesoscale bands persist in the region from central Massachusetts down to eastern Long Island and extend northward towards New Hampshire. Recall we observed deformation in the visible imagery earlier over this region where these mesoscale bands exist. In that same visible imagery, we also noticed a region of thinner clouds in western Massachusetts that's supported by this lack of reflectivity across this region in the later portion of the loop. However, we do observe echoes in southeastern New York City region, but these are less intense than those further to the east, in part due to that cold, drier air mass at low levels that we observed on the Albany sounding. We see an enhancement of echoes for a few hours in the Albany region that apparently is tied to a local terrain-driven convergence zone that's not observed in the satellite imagery. The lower clouds are probably obscured by higher level clouds. And then finally note we see these transverse bands in this region just east and southeast of Boston. Here's the hourly radar loop to summarize the event. Early on, we see a broad shield of precip moving into the forecast area associated with that secondary warm conveyor belt. From early on, we notice a sharp reflectivity gradient along the western edge of the system, owing to the low-level cold dry air mass. We also observed mesoscale bands soon after the onset of precipitation. We observed convection with higher reflectivities off Nantucket to the north of the surface low. Recall on the IR loop, we observed that convection as it moved onshore. Later, we see a transition from the more uniform aerial coverage of echoes to these spottier but still very intense echoes as the secondary warm conveyor belt / trough moved northward. On a larger scale, we observe a mesoscale snowband from Maine to eastern Long Island with the deformation zone that we saw in the visible imagery. This gradually shrinks with time, though still leaving narrow regions of smaller bands of heavy snow. And then finally, near the end of the loop, we see the low-level circulation approaching the Gulf of Maine and slowing down. Areas of enhanced echoes remain on the backside of this low, persisting for several hours before the low finally moves northeast, introducing the cold and dry air mass. As we alluded to earlier, with the introduction of GOES-R, we're going to have one-minute imagery much more often with these type of intense winter storms. So for this particular example that we're looking at, this is during the GOES-14 science test, where we collected one-minute imagery on this storm, which provided for a lot of snow across a pretty broad region. These are some of the things that you'll be able to see. They just show up a lot better. You'll have more images to look at. You see them, you'll get them on your AOIPS a lot faster, within about a minute. In this particular example, you can see the surface low quite nicely. It looks like we have an occluded front just on a short segment to its northeast, and then followed by the cold front that's coming around in this direction. So further to the northeast, we would have our warm front. In this region, we can see the development of these mesoscale bands in eastern Virginia, extending up through the Chesapeake Bay region, and they just show up a whole lot better in terms of the development and evolution of these bands. You can match this with your radar a lot better here. The other thing to note is you can see the clouds at different levels, the low-level clouds with the mid-level clouds over the top of them. You can see very strong northerly winds on the back side of the low in the later portion of the loop. So again, it'll give you a better contextual understanding, a better situational awareness, therefore, of what's going on in the imagery here, and you'll be able to compare that with your radar, lightning, and other data sets. In conclusion, we identified regions of greater short-term NWP uncertainty via the Schreff plumes. We looked at synoptic scale features identified on satellite that led to the evolution of the strong cyclogenesis event. And we utilized a blend of the RSO Satellite Imagery, radar, and other observational data for these mesoscale details. And we also are looking forward to the introduction of GOES-R, when we'll have even higher resolution, either 1 minute or 30-second data, quite often for these big storms. So you'll be able to see things that you just haven't been able to look at in the past. As you look at the 1 minute imagery more and more frequently, you'll be able to see additional details.